Probability of simple events. We'll begin by discussing what a sample space is, which is a set of all possible outcomes for an activity or experiment. A sample space is usually denoted using set notation, which are also shown in between these braces, or sometimes people call them curly brackets. And the possible outcomes are listed as elements in the set. So A, B, C, and so on all the way up to Z could be elements within a given set. A variety of activities are shown in the table. Find the sample space for each activity. And again, the sample space is a list of all possible outcomes. So in this spinner, someone could spin blue, red, green, or yellow. So we're going to put each color in a list inside of braces. So they did yellow, blue, red, and green. In this one, we are flipping 2 coins. They end up being dimes. You could get heads in both. You could get heads on one, tails in the other. As it currently shows, you could have tails for the first and heads for the second, or you could have both be tails. So if capital H represents heads and capital T represents tails, the possible outcomes could be HH, HT, TH, and TT. Now we have a die, or a number cube. There are 6 different sides of the die or number cube, so the possible outcomes are the numbers 1 through 6. In this next one, we have marbles or gumdrops that are inside of a cylindrical container, and they have various colors. You could have yellow, green, or red. So our sample space is yellow, green, or red. Now this last one, we're rolling 2 dice, or 2 number cubes. So you could have 1 1, 1 2, 1 3, 1 4, 1 5, 1 6. You could do 2 1, 2 2, 2 3, 2 4, 2 5, 2 6, 3 1, 3 2, 3 3, 3 4, 3 5, and 3 6. Whereas where the first number in each ordered pair represents the cube to the left, and the second number represents the cube to the right. And it continues. 4 1, 4 2, 4 3, 4 4, 4 5, 4 6, 5 1, 5 2, 5 3, 5 4, 5 5, 5 6, and 6 1, 6 2, 6 3, 6 4, 6 5, and 6 6. If the outcomes in a sample space are equally likely to occur, the theoretical probability of an event, denoted as capital P, and then the event being in parentheses, is a numerical value from 0 to 1 that measures the likelihood of an event occurring. You can write the probability of an event as a ratio, decimal, or percent. So the probability of an event is equal to the number of favorable outcomes divided by the number of possible outcomes. An event with a probability close to 0 is unlikely to occur. An event with the probability that is close to 1 is likely to occur, and an event with a probability of 1/2 is just as likely to occur as to not. For example, the probability of flipping heads using a fair coin is 1/2, and the probability of flipping tails with a fair coin is also 1/2. Here's an example that is non-geometric that goes over the theoretical probability based on a sample space. There are 7 red marbles and 3 green marbles in a bag. 1 marble is chosen at random. Write the probability that a green marble is chosen. Since there are 3 green marbles in the bag, our numerator in our fractional answer will be 3, and the denominator will end up being the total number of marbles. If there are 7 red and 3 green ones, then there is a total of 10. So our answer as a fraction is 3/10. As a decimal, that's written as 0, then the decimal point, and a 3 afterwards. This is 3/10. And as a percent, that's going to be 30%. And remember, when converting decimals to percents, you're multiplying the decimal value times 100, or moving the decimal point 2 places to the right. Here's another example. Our sample space is choosing a card from a standard deck, and there are 52 cards in a standard deck. There are 13 cards in each suit, so there are 13 hearts, 13 diamonds, 13 spades, and 13 clubs, and there are 4 of each numbered card or face card. So we have an ace, which is kind of like the number 1, then we have 2, 3, 4, 5, 6, 7, 8, 9, 10, and instead of 11 we have jack, instead of 12 we have queen, and instead of 13 we have king. And suppose you choose a card from the deck. What is the probability of pulling a heart from a standard deck of cards? Well, we have 13 hearts to choose from, so that's going to be our numerator, and our denominator is the total number of cards in a deck, which is 52, and now this reduces to 1/4. You could also write the final answer as a decimal, which is 25 hundredths, or as a percent, which is 25%. Now, what's the probability of selecting a 3? Well, here are all of our 3s, and there are 4 of them, so our numerator is going to be 4, and our denominator is going to be the total number of cards in a deck, so that's 52, and we can reduce this to be 1/13. And our final question is, what is the probability of drawing a 4 of spades? Well, there's only 1 4 of spades, so it's 1 out of the total number of cards in a standard deck, which is 52. And our answers definitely match what is shown. Now let's discuss the probability involved in a number cube or a die. We can see that we can roll it and you get a random number. So our sample space that we have are all of the possible outcomes that could come up. So you could roll a 1, you could roll a 2, you could roll a 3, you could roll a 4, you could roll a 5, or you could roll a 6. So our sample space are those curly brackets or braces with the numbers 1 through 6 in between. Now let's find the probability of each event. The probability of rolling a 2 is 1 outcome, is only a 2, out of a total of 6 outcomes. So the probability of rolling a 2 is 1/6. Now let's look at the probability of an even number. Well, the even numbers are 2, 4, and 6. There are 3 of them. So the probability of rolling an even number is 3 out of 6, which reduces to 1/2. Now let's find the probability of rolling a prime number. A prime number is any number that only has 2 factors, 1 and itself. 1 is not considered a prime number because it only has 1 factor, 1. 2 is a prime number because its only 2 factors are 2 and 1. 3 is also a prime number because its only factors are 1 and 3. And 5 is also a prime number because its only factors are 5 and 1. Now 4 and 6 are both considered composite numbers because 2 can divide into 4 and 3 can also divide into 6, aside from 1 and the number itself. Therefore, the only prime numbers in this set are 2, 3, and 5, meaning we have 3 potential prime number outcomes out of the total 6, which also reduces to 1/2. Now let's find the probability of a number greater than 4. Well, greater than 4 only occurs for the numbers 5 and 6. So there are only 2 possible outcomes that satisfy that condition out of the total 6, and if we reduce our fraction, it reduces to 1/3. And here we can see our solutions do match up with what we found. Here's another probability example. We have the spinner with the colors green, red, orange, and purple. And if we spin it, we can see that the spinner is landing on different colors each time, which is generally what happens when you use a spinner, say, in a board game or any type of game. So the sample space for this problem would be red, orange, green, and blue. And again, we put them inside of the braces or the curly brackets. And now we're going to find the probability of each event. What's the probability of spinning green? Well, it makes up a quarter of the circle, or you could consider it as there are 4 outcomes and green is one of them, and they are all equally likely, so it's 1/4. Again, you can also look at it in terms of the area of the part that satisfies green to the whole thing. And now the probability of orange is going to be the same thing. There's only one orange sector, and there are 4 total sectors in all. So the probability of spinning an orange will also be 1/4. Here's another probability example. We have a quarter or $quarter coin, and we are finding the sample space for the activity that is given if we flip this quarter. Well, the total potential outcomes, it could land heads up or it could land tails up. So we could write H and then T, H for heads, T for tails. And now let's find the probability of each event. The probability of flipping heads would be 1/2, and the probability of flipping tails will also be 1/2 because the coin is equally likely to land on each side. We have evaluated probabilities by counting the number of favorable outcomes and dividing that number by the total number of possible outcomes. In the remaining topics of this unit, a related process in which the division involves geometric measures, such as the length or area, will be used. This process is called geometric probability.